Okay, for the last part of formation of colored compound in a transition element topic, okay, is the factors affecting the stability of complex. Okay, how to determine the stability of complex. Okay, we take a look one by one. Okay, for the first one, okay, we can see the type of ligand. Okay, for ligand, it have two pattern here. Okay, so for the first one is a chelating agent. Okay, chelating agent. Chelating ligand. It's more stable, than non-chelating ligand. So what is chelating ligand? Okay, chelating ligand is the example like EDTA, alright, and then ethyldiamine, oxalato, alright. So that one is the chelating ligand, which is it's more stable compared to non-chelating ligand like water, ammonia, chloro. Okay, that one is non-chelating ligand. Okay, the second one is a strong field ligand. Is more stable than weak field ligand. Okay, now we take a look at the example here. Okay, for the first example, okay, it both using the iron 3 plus. Okay, so centrometal is the same centrometal, which is iron 3 plus. Okay, we refer to the ligand here. Okay, for the first one is it use oxalates ion. Okay, so this oxalate ion is a chelating ligand. Okay, this is the chelating ligand. Okay, while the second ligand is a non-chelating ligand. Okay, so which complex ion are more stable? Okay, for sure, for the first one, which is tris oxalato iron 3. Okay, iron 3 iron. Okay, this is the most stable compared to hexa aqua iron 3 ion. Okay, so this one is a more stable. Okay, second example here is, okay, we have the complex ion which contain of both, okay, cyano and chloro, both are non-chelating ligand. Okay, but for cyano ion, okay, for cyano here is a stronger ligand. So Cn ion is a stronger ligand compared to chloride ion. Okay, so that's why since it share the same centrometal, okay, which is nickel 2 plus, so this complex ion which is tetracyano nickel 2 is more stable compared to tetrachloro nickel 2 ion. Alright. Okay, so we refer to the stronger ligand or weak ligand in the complex ion. Okay, now the second factors that affecting the stability of complex is oxidation state. Okay, oxidation state of central metal ion, which is central metal ion with a higher oxidation state is a more stable compared to the central metal ion with a lower oxidation state. Okay, so we take a look at the example here. Okay, so we are given the two complex ion, okay, which is the first ion is consists of iron 2 plus, alright. 3 plus, so 3 plus. Okay, and then the other one is iron 2 plus. Okay, since the both complex ion is share the same ligand, which is aqua ligand, so how to compare the stability of the complex ion? We use the oxidation state of ion, okay, which is the higher oxidation state is more stable compared to the lower oxidation state. So that's why the hexa aqua iron 3 ion is more stable than hexa aqua iron 2 ion. Okay. Alright, okay, and then the third factors that affecting the stability of complex is the size of metal ion. Okay, if the ion have a same oxidation state, okay, and same ligand here, Okay, same oxidation state. So how to compare the stability of complex? We take a look the size of metal ion. Okay, which is the smaller size. Okay, the smaller size of metal ion is more stable than larger size of metal ion. Okay, let me see the example here. Okay, for the example here, okay, we have okay, a few of complex ion here. Okay, across the transition element, across the period here. Okay, so let me draw. Okay, so here is the across the period. We know that the size are getting decreasing. Okay, so starting from we have vanadium. Okay, we have vanadium. Okay, we have chromium. Okay, we have manganese. Okay, we have iron, we have cobalt here, we have nickel and copper. Okay, so from this list of transition element, you can see that copper is the smallest size. Okay, followed by nickel, cobalt, iron, manganese, chromium and vanadium. Okay, so if the complex ion are shared the same ligand here, okay, the same ligand which is in this question is shared the aqua ion, so the water ligand. Okay, the four of the complex ion okay are bonded with the aqua ligand. So how to compare the stability? Okay, so we take a look the ligand, the central ion that used here. Okay, since okay all the central ion here is the same okay, use the same oxidation state which is copper 2 plus, okay, nickel 2 plus, okay, and then cobalt 2 plus and also iron 2 plus. So to compare the stability of the complex, we refer to the ion size, which is okay, copper is the smallest, okay, since copper is the smallest, so it has the highest stability. So that's why it is the most stable compared to nickel ion, cobalt ion. Okay, so the most stable of this compound is copper, okay, hexa aqua copper 2 ion. Okay, followed by hexa aqua nickel 2 ion, followed by hexa aqua cobalt 2 ion, and the last one, the least stable here is the hexa aqua iron 2 ion. Okay, stability of complex is okay is equilibrium constant of complex, which is K stability. Alright, so for equilibrium constant of complex, okay, which is the higher the K stability, the more stable of the complex. Alright, so the higher the K stability, the more stable the complex. Okay, let me see the example here. Okay, so now, okay, here is the example of chemical equation. Okay, to be compared. Okay, so the first, for the first equation is I give that the hexa aqua of copper. Okay, when it react with hexadentate ligand, so now it will form the complex EDTA. Okay, EDTA complex. Okay, so how to calculate the equilibrium constant? Okay, actually is like okay how we measure the other equilibrium constant, right, which is the product over the reactant. Okay, in order to calculate the equilibrium constant, okay, so we just divide the product, okay, this product, okay, over the reactant. So which is in the first chemical equation, it have two reactant, so 1 and 2. So we just write down like this. Okay, and then the reading, okay, of K stability given is 6.3 times 10 power of 18 dm cubic per mole. Okay, now we refer to the second chemical equation, okay, which is involved of hexa aqua copper 2 ion, okay, which it react with the monodentate ligand, which is ammonia. Okay, so it will form the complex. Okay, it will form the complex here. Okay, the new complex here. Okay, so in order to write down the K stability here, okay, for the ni, okay, in order to write down the K stability, okay, we just write down the product over the reactant. Okay, since the second equation consists of one product, so we just write down the product, okay, over the first reactant here, okay, and second reactant like this. Okay, okay, but for the second reactant, if you can see that it have coefficient for ammonia ligand. So what happen is when we write down the K stability, we must power off the coefficient, which is power of 4. Okay, for ammonia ligand. Okay, so finally we get the K stability value given is 1.2 times 10 power of 12 dm cubic per mole negative 4. Okay, so refer to the value. Okay, now we can tell that the reading, okay, the K stability of the first equation is much more greater than the second equation, which is 1.2 times 10 power of 12. Okay, so what is the conclusion that we can make is the higher, okay, the higher the K stability, okay, so the more stable, okay, the more stable the complex. So which one is the most stable one? So this product is the most stable compared to the second complex product. Alright, okay, so that's all for this time. Okay, thank you.